All right, welcome to this lecture in algebraic topology. Today we're going to talk about polyhedra and Euler's formula, one of the most famous formulas in mathematics. So the story of polyhedra goes back to the ancient Greeks. They were particularly interested in 5 basic objects, which we've already mentioned, the Platonic solids. And these are the polyhedra that are very regular in a precise way. So a polyhedra, or a polyhedron, is a 3-dimensional object made of polygonal faces where the two faces meeting 2 at a time, meeting along edges, or perhaps at a vertex. And there are a lot of different types of polyhedra, and we're going to talk about some of them in this lecture. And we're going to especially be interested in polyhedra which are roughly topologically the same as a sphere. And for those, we're going to establish Euler's fundamental formula between the number of vertices, edges, and faces. So let's talk about the polyhedra, the Platonic solids. The Platonic solids are characterized by a great amount of regularity. So each face is a regular polygon, and all the faces are identical. But it's a little bit more regular than just that. It's also the case that also each edge and each vertex also look the same. Also each edge and vertex look the same. In other words, there's no way, say if we take our favorite one, the dodecahedron, there's no way of distinguishing this vertex from any other vertex, and there's no way of distinguishing this edge from any other edge. Now this particular model of the dodecahedron doesn't really show its solid nature quite so well as perhaps this kind of model made out of what's called polyhedron. So this is called polyhedron, where you have these shapes that snap together. It's a lovely investigative tool for mathematicians. Here we can see the faces very clearly, and they're solid. And here the faces are a little bit invisible, but we can see the overall structure a little bit clearly because we can see through it. This system is called Zohm construction system. That one is called polyhedron. They're both excellent tools to play around with. Okay, so what are the 5 Platonic solids? Well, we have to list them. So the first one is the tetrahedron, and then there's a cube, and then there's an octohedron, and then the icosahedron, and finally the dodecahedron. And we'll make a little table here where we list the number of V for vertices, E for edges, and F for faces. Okay, so the simplest one perhaps is the tetrahedron, made out of 4 equilateral triangles. So it has 4 triangular faces. It's got 4 vertices, and it's got, well, an edge rather, from each vertex to another. So there's 4 choose 2, or 6 edges. That's a tetrahedron. The next, probably the most familiar one, is the cube. The cube has 1, 2, 3, 4, and 4, it's 8 vertices. it's got it's got 4 edges along here and 4 edges along here and then 4 edges along the sides, so there's 12 edges altogether. And it has 1, 2, 3, 4, 5, 6 faces, each a square. Then after that we have the octohedron. The octohedron has 4 vertices in a plane forming a square, and then 1 vertex above and 1 vertex below, so 6 vertices altogether. Altogether 4 edges emanating from here, 4 edges emanating from here, and 4 in the middle, so that's also 12. And faces, we have 4 triangular faces at the bottom and 4 triangular faces at the top, so 8 of them altogether. It's the octohedron. The icosahedron is made up of triangular faces. And, well, how many vertices are there? Let's put them like this. So there's 3 on the bottom and 3 on the top, and then there's a sort of a ring of 6 around the middle. So we have 12 vertices. Counting edges, well, let's see. There's 3 in this base triangle, 3 in this base triangle. And then there's sort of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, hang on, did I say that right? Well, if you count them, there's 30 of them. Okay, maybe it's a little bit hard to say exactly how to count them, but there are 30 of them. And how about faces? Okay, there's 1 face at the bottom, 1 face at the top, and then there's a kind of a ring of faces. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 at the bottom, 10 at the top. All right, let's do that. 20 faces altogether. Once you've counted the faces or the edges, you can get from one to the other by observing that, let's say you have 20 faces, and you want to know how many edges there are, then each face will contribute 3 edges. So each face is contributing 3 edges, so if there's 20 faces, then there's 60 edges, but each edge is being counted twice, because this edge here is counted in this face and this face. So we have to divide that 60 by 2. So we can go from here to here once we've gotten one of those. I find the dodecahedrons easier to count. So here it's pretty obvious that there's 5 vertices on the bottom, 5 vertices on the top, and then we have this nice little up and down ring of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this middle sort of layer. That middle ring, by the way, that I've just pointed out, going up and down, it has a special name in Platonic or in theory of polyhedra. It's called a Petri polygon. It's a polygon on the surface of the polyhedron that alternates going left and then right. So if you go along an edge and then you take a sharp left turn, and then at the next intersection you take a sharp right and a sharp left and so on, then back to the original, then you're forming this polygon like this, called a Petri polygon. Okay, so we counted the number of vertices was 20. And the number of faces, that's not so hard because there's 1 on the bottom, 1 on the top, and then there's sort of 5 joining the one up on the top and 5 joining the one on the bottom. So there's 12 faces. And each face, of course, is a pentagon, has 5 sides. So one way to count the edges would be so there's 5 times 12, that's 60 edges, counting each edge twice. By the same idea as before. And so we divide that by 2, we get 30 again. All right, so that's a basic counting business. And we see that there's some duality that I've mentioned also already. These two objects here are duals in the sense that if you take the centers of the faces, then you get an octohedron. And conversely, if you take the centers of the faces here, then you get a cube. And the duality is reflected in the fact that the number of vertices here is equal to the number of faces here, and so on. The duality also extends to the icosahedron and the dodecahedron. It's the same story that we've already talked about. If you take the middle of the faces of the dodecahedron, then you get an icosahedron. If you take the middle of the faces of the icosahedron, then you get a dodecahedron. And that's why those numbers are also symmetric. Why this 12 agrees with that 12 and that 20 agrees with that 20. So these are also dual. What about this tetrahedron? Well, it's kind of dual to itself. If you take a tetrahedron and you take the centers of the faces, and you get another 4 points, and if you join them, you get a smaller tetrahedron. So it's self-dual, reflected in the symmetry between the vertices and the faces. Okay, so these have been studied since ancient times. The Greeks were very interested in this, and they constructed these things rigorously. One should make the important comment that just because one can make a model of such a thing does not mean that it really exists as a mathematical object. Okay. If you actually make this out of either Zohm or Polyhedron, you see that at some point the thing becomes rather rigid. Before you've actually finished it, it becomes rigid. And then it's almost like a lucky accident that the last piece fits in. Right? So it's actually theoretically possible that this does not actually exist as a mathematical object, but only as an approximate physical one. In fact, it might be, for example, that if you actually measured it accurately, that there's a slight, that we've had to bend something to make things fit. Or we've had to shorten or stretch just a little bit. But the ancient Greeks proved that that was not the case, that it was actually a real object mathematically, not just physically. So it's rather remarkable then that, that Euler, the greatest mathematician of modern times, Leonhard Euler, was the first to stare at these numbers and realize that there was an interesting pattern or formula to them. He realized that we could define a number which is usually now called chi, which is the number of vertices minus the number of edges plus the number of faces, and that we always get 2. It's completely remarkable that this was in the middle of the 18th century before this fundamental and beautiful fact was discovered. So anybody prior to that could have become eternally famous by having made this simple observation, but they didn't. It had to wait till the greatest mathematician of modern times to actually do it. Okay, so you can quickly see that it's true. And Euler wrote, I think, a couple of papers on this, not a lot. In his first paper, he mentioned this fact, but he said he didn't have a proof of it. And then in his second paper, he established a proof of it. But the proof was criticized by people. Euler's proof was clever, and the story it's a very nice story, and I recommend the following book by David Richardson, a book called Euler's Gem, where the story is told very, very nicely. Euler's original proof involved taking a polyhedron and cutting it, sort of slicing off tetrahedral portions and sort of making clever series of reduction until you end up with a very simple thing, keeping track of what happens to the vertices, faces, and edges as you make this deconstruction. But it was a little bit criticized by people who came later because Euler wasn't too clear about the sequence of constructions that you had to make. He didn't say what exactly you had to do after each other, and it's possible, if you misinterpret his instructions, to cut the thing up so that at some point it falls into 2 pieces. to disconnect it. And if you do that, then things go a little bit wrong. So there was a little bit of a problem. And in fact, this theorem has had a very interesting history in terms of its proofs. People have realized that it doesn't always work. Well, it works certainly for the Platonic solids, but if we try to generalize it to more general polyhedron, it's a little bit subtle, and sometimes it works and sometimes it doesn't, and finding proofs that work for all the cases that are known was a delicate issue. There are probably more than a dozen, maybe 24 proofs that have been shown. So we're going to talk about a proof today, but before I do that, I want to introduce some other types of polyhedron. Not just these Platonic solids, there are also another very rich family of solids called the Archimedean solids. Okay? They're not quite as regular as the Platonic solids, but they're still very interesting. The Archimedean solids. So these were discovered by the greatest mathematician of antiquity, Archimedes. But unfortunately, his writings on the subject have been lost, and so we only know about it indirectly. They were rediscovered by Kepler. And probably by several other people since then. Okay. So what are the Archimedean solids? Well, they are polyhedra, whose faces are also regular polygons. So for example, this one here that I have has some squares and some regular hexagons. It's all just made of squares and regular hexagons. And so the faces are not all the same, but they can be of different types. So different types. But the regularity is in the sense that all the vertices look the same. All the vertices look the same. So if you take any one vertex here, say that one there, it's got touching one square and two hexagons. And any other vertex has the same property. You can't tell any vertex from any other. That's not the case for edges, right? You can tell that that edge there between two hexagons is of a different nature than that edge there between a hexagon and a square. So we'd say that the group of isometries of this thing would be transitive on the vertices. In group theoretic language, we would say that. Okay, so how many of these are there? Well, there are 13 of these. There are 13 of them. Although sometimes there's a little bit of ambiguity because two of them have a special nature. Two of them are chiral in the sense that there's a sort of mirror images of them possible. There's something called a snub cube and a snub dodecahedron, which you get by essentially rotating. Say if you take a cube and you rotate its faces a little bit and then you leave some spots and you can stick triangles in. But then you have a choice of whether you want to rotate this way or that way. So there's sort of two versions of it. So by some accounts, maybe there's 15 of them if you count the mirror images. Okay. But in any case, so where did the Archimedean solids come from? The easy way to think about it is you just take your favorite Platonic solids and you truncate one of the vertices. Okay, so let's say we take our dodecahedron here, and at each vertex I'm going to chop off a piece, chop off a slice. But I'm going to do it in such a way that the piece that I'm chopping off here, right over here, is going to form a regular polygon with this one here. All right, so we can get the Archimedean solids by truncating. So they are formed by truncating the Platonic solids. Plus doing some other things. Now, in 1619, Kepler wrote a book, Harmonici Mundi, which is something like the harmony of the world, in which he discovers the 13 Archimedean solids and actually gives very nice pictures of them. So when I can actually look at this book in 1619 and actually find beautiful pictures of these 13 Platonic Archimedean solids. In particular, there's one that's particularly famous, perhaps the most famous one. Especially if you're a fan of soccer, is a soccer ball. So while soccer balls come in different forms and patterns, as we know from the recent World Cup, but in the last 20 or 30 years, there's been a kind of an established shape for these things in terms of hexagons and pentagons. And that's created by, that's called a truncated icosahedron, where we take an icosahedron and we lop off a segment near each vertex. So what's going to happen there? Well, what's going to happen is that, okay, we do it in such a way now that what's inside here, instead of being a triangle, it's now going to be a hexagon, a regular hexagon. And since there are 5 edges coming to a vertex, when we chop that off, we're going to get a pentagon there. So we get a shape with 12 pentagons. One for each of the vertices of the icosahedron, and 20 hexagons. One for each of the faces, the triangular faces of the icosahedron. So this is a soccer ball. But it also has another incarnation, which is rather more recent, in the 1980s, perhaps 1985, thereabouts. It was discovered, astronomers discovered a new form of carbon out in the distant part of the universe. They discovered that there were certain processes in stars that created a new form of carbon, or a new arrangement of carbon atoms. And they were able to deduce what this thing should look like as a kind of a complicated molecule. New arrangement of carbon atoms, where we have 60 carbon atoms. So that's how many are going to appear in this thing. Okay. So 60 of them are arranged at the vertices of this Archimedean solid. 60 at the vertices. And okay, this was then subsequently actually produced in laboratory by chemists and given a name, and it's, well, there's sort of a family of these things, but they're called fullerenes, or Buckminster fullerenes, for a famous architect, engineer, inventor who created the geodesic dome in the 1967 Olympics. The US pavilion was a geodesic dome, and so in honor of him they call these things fullerenes. And it's generated quite a lot of interest in chemistry and other places. Okay, so we just observe here that if we take the Euler number for this truncated icosahedron, well, the number of vertices we've said is 60. The number of edges, it turns out to be 90, yes, 90 edges, thank you. And the number of faces, well, we have to add these two together, 32. we still get 2. So Euler's formula doesn't just hold for the regular solids. In fact, it holds for arbitrary polyhedra, which are roughly the shapes of spheres. It only became slowly clear that that was the right way of thinking about Euler's fundamental formula. That we should think about it as a topological quantity. So Euler's formula holds for any polyhedron, which has the topology of the sphere. So in some sense, it's actually really ultimately a theorem about the sphere. So how can we connect it with the sphere? Well, of course, if we have any of the Platonic solids, we can embed the Platonic solid in the surface of a sphere. We can imagine, for example, a light bulb in the middle of the Platonic solid. We can imagine a big sphere around it. Imagine the shadow of the Platonic solid from the light bulb in the middle on the surface of the sphere. That would then give us a rounded version of the Platonic solid on the surface of the sphere. Okay. And in terms of counting edges and faces and vertices, it doesn't really matter whether we work with that rounded object or with a flat object originally. All right, so that's an important idea, that we can think of a general polyhedron which has the topology of the sphere as a bunch of polygons on the surface of the sphere. Okay, so let's draw this. We'll kind of draw rather rounded edges to let us keep in mind that we're on the surface of the sphere. So we've got some arbitrary pattern of polygons, and they don't have to be regular now. And they don't have to all be the same number of vertices. Okay, and this thing goes all the way around, covers the entire sphere. Okay. And what we want to do is we want to prove that for such a sometimes it's called a complex of polygons on a sphere, that if we count the number of vertices, subtract the number of edges, add the number of faces, we get 2. So I'm going to give you a proof. Which will introduce some other interesting ideas that are going to be important for us. So the proof amounts to, first of all, we would like to replace these rather arbitrary polygons with rather nice triangles. Okay? So we're going to fill in the polygons by triangles. Okay, in what way? So what we're going to do is we're going to do a number of things. We're going to possibly introduce a new vertex. We'll just introduce a new vertex along an edge. Okay. If we do that operation, then we've increased the number of vertices by 1, and we've increased the number of edges by 1, because instead of having one edge here, we now have 2 separate edges. So obviously this quantity hasn't changed. So we can add vertices as we like, and creating new edges as we go. And then the second thing that we're going to do is we're going to join vertices with new edges. So for example, I might join that one with that one. What have I done? I've now increased the number of edges by 1. And I've increased the number of faces by 1, because instead of having one face here, now there are 2 faces. So if I've increased the number of edges by 1 and increased the number of faces by 1, then this quantity hasn't changed. So the quantity v minus e plus f is unchanged by this kind of subdivision. And now I just keep doing that. Until I've got lots of triangles. Okay, my example so far, have I got triangles? Not quite yet. There's one more. Oh, that was the equator. Okay, just keep doing it until the polygons are now lots of little triangles. And we make sure that the triangles are small. Well, small in relation to the sphere. I don't want any really big triangles. So if we have a really big triangle, let's say we think this one is really big, well, we can just subdivide that one into smaller triangles, and those ones into smaller triangles if necessary. So by keeping on dividing triangles into smaller triangles, we can ensure that all the triangles, we're covering our original net with lots of little triangles, but the quantity v minus e plus f has not changed from what it was initially. Okay. All right, so now we have a complex consisting only of triangles, and we are going to now try to count what is v minus e plus f. So to count that, what we're going to do is we're going to put a little plus sign on each vertex, a minus sign on each edge, and a plus sign on each face. You can almost think of like a little particle, an electron or a proton. Okay, so so there's lots of them. So we'll put little pluses on each of the vertices. And then we put little minuses, say in the middle of an edge. Okay, so every edge gets a little minus sign, which is actually sitting over, you can think of it sitting right on the middle of the edge. And then each face gets a little plus sign, right in the middle of the face. And now it's clear that this quantity v minus e plus f is just the total of pluses and minuses added together. Think of the plus as being plus 1 and the minus as being minus 1. So we want to show that the total is equal to 2. All right, now what we're going to do is we're going to flow these charges. Now, I think this argument goes back to William Thurston, who's one of the most prominent algebraic topologists of the 20th century. It's a very nice argument. We're going to flow these charges. And the way we're going to flow it is we're going to, rather arbitrarily, introduce a north pole somewhere and a south pole on our sphere. And the north pole and south pole are going to give us lines of longitude. Okay? If that's the North Pole and that's the South Pole, then a great circle that goes from the North Pole to the South Pole, that's a line of longitude. And there's all these lines of longitude. Just the intersections of the planes of the sphere with planes through the origin, through the North and South Poles. So we've got all these lines of longitude that we can flow on. So basically what we're going to do is we're going to use gravity. We're going to just imagine this thing is in space, and we're going to flow things down. Okay, so we're going to flow downwards. Okay, so we have our frame of triangles, our complex of triangles. We have our north pole and our south pole, and let's put the north pole up here. So there's our north pole. Let's arrange that the north pole is not on the complex, so it's in some particular face. And we'll arrange that the south pole, which is on the back here somewhere, is also in some triangular face at the bottom. Okay. Now, the question is, what happens when we flow the charges down? We're not going to flow them very much. We're just going to flow them a little bit, so that the charges on the vertices are going to flow into an adjacent face, and the charges on the edges are going to flow into an adjacent face. And as soon as they get into a face, they're going to stop. It's not a big flow. They're just going to move a little bit. We're just going to give them a little push down. The charges that are in the middle of the faces, we're going to leave them where they are. So what happens? So flow the charges a little bit downward. So off the vertices and off the edges into the faces. Okay, so let's just look at one particular triangle. So here's a triangle in our triangulation, and the flow lines are, well, this is a very little triangle, so the flow lines are all sort of like that. Okay, they're pretty well parallel as far as we're concerned, because we're just in a very small part of the sphere. Okay, now what we have? We have plus signs at each of the three vertices. We have a plus sign in the middle of the face, and we have minus signs on the middle of these edges. Now I want to flow down. So what's going to happen in this case here is that this edge is going to flow down into that face. This edge is going to flow into something else. This vertex is going to flow into something else. This edge is going to flow into something else. And the only thing that's going to end up, and these guys here are also going to go out. The only thing that's flowing into this face is this negative sign. Okay, that's one possibility. Another possibility is that the triangle is oriented like this. Oh, sorry. With our flow lines. Okay, so there's a plus sign in the middle, plus, 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 minus, minus, minus. In this case, this minus sign is going to flow in, this plus sign is going to flow in, this minus sign is going to flow in. These other ones are going to go out. So in this case, this one flows in. In this case, these three flow in. In both situations, the net result is 0 in the middle of that face. We had plus sign here and one minus sign coming in. That gives a net of 0. Net equals 0. And over here, we had plus sign to begin with, and two negatives came in and one plus came in. So we still get a net of 0. Now, there's a slight technical problem, though. What happens if one of the edges of the triangle was perversely exactly along a meridian line? then we agree that there's some kind of problem, because that minus sign is not going to, if we flow down, it's not going to flow off the edge. So we have to arrange beforehand that that's not going to happen. And the way we arrange that beforehand is just by jiggling our pattern. Okay? If this edge is exactly along here, if we just move the pattern a little bit, then that edge is no longer going to line up with the meridian line. So we need perhaps to jiggle the complex so no edge, no triangle edge is up and down or along a meridian. Which we can clearly do. We could also, I suppose we could subdivide it, but that's a kind of common argument that we're just talking about topology. We're only counting, so if we move things a little bit, the numbers of vertices, edges, and faces hasn't changed. Okay, so we started off with this complex. We've assigned plus and minuses to the edges, vertices, and faces, and now we've flowed them. And now what happens? What's the final result? Well, the final result is almost every triangle has a total of 0 charges inside after cancellation. After cancellation, most triangles, in fact almost all triangles, most triangles have a net charge of 0. But there are 2 exceptions. What are the 2 exceptions? They're the 2 triangles that we started with, which contained our north and south poles. Our flow is starting from the North Pole. That's our source of the flow. And the flow is ending at the South Pole. That's the sink of the flow. And what happens for those 2 triangles? Well, for the North Pole, there was a plus sign in the middle. And all its charges on the boundary leave, because we're flowing down away from the North Pole. So at the end, there's still a single plus sign in that northern triangle. What about the southern triangle? Well, it had a single plus sign in it, and all of its boundary charges flowed into it. They all went in here. Now there are 6 vertices and 6 edges, 3 edges and 3 vertices. So altogether, plus, minus, plus, minus, plus, minus have flown in. They all cancel, and we still end up with 1 total for the south. So only the north and south triangles, let us say, have a net charge of 1. And so we can say, conclude, so the total charge must have been, well, 1 plus 1, which is 2. And so there's a proof of the Euler formula that holds for any complex that you can build on the surface of a sphere. And implicitly has some ideas that are going to be important to us later. The idea of flowing, the idea of a vector field, the idea of sinks and sources. We're going to jack this argument up eventually to deal with other surfaces than just the sphere. But this is a good starting point for that sort of a sequence of ideas. All right, so next time we're going to look at another approach to Euler's formula relating to graphs. And I'm going to show you, in fact, a much simpler, no doubt the simplest possible proof of the Euler formula, which is very clear when you think in terms of graphs rather than polyhedrons. And that will connect to a number of interesting planar mathematics. So next time, graphs and the Euler number again. See you then.